I've had the privilege of visiting Future Hope School. That was almost exactly a month ago. I think I was there in early September when there's Sunny. I'll introduce Sunny after Future Hope. Future Hope is a school in the city of Kolkata, city I grew up in. When was Future Hope founded? I'm going to ask the Future Hope students to tell me a little bit about their school. When was your school founded? Which can the students at Future Hope hear me?
Yeah,
go ahead.
1987.
1987. Okay. So it's been 36 years. That was 2 years after I left Kolkata to go to graduate school on the East Coast in Princeton. Please, if you could tell me which grades or which classes each of you is in. If you could just take the microphone around and go around. I want to get a sense of how old you are and which class you're studying in. Let's start with yeah, go ahead.
Class 698.
Class 6
and 8. 8. 6 and 8.
9, class 8?
6 and 8.
6 and 8. I see. So how old would you say that is? Is that 14 and 12? 12 and 14. Okay. How many students are in the room there? I think I've been to this library. How many students in your room right now?
More than 18.
18 students?
Around 40.
Around 30. Okay.
Around 40.
40. Okay. It is, if I'm not mistaken, it's close to your lunchtime now, right? It's 11:40 in India right now. 11:39. What time is your lunch
At 1:10.
break? 1:10. Okay. Are there any teachers in the room with you, or is it only students? Hello.
How are you?
I'm good, thank you. How are you? Thank you
I'm
for
good.
connecting. Oh, we have 2 teachers in the room. Hello. So say a little bit about the experiment we're doing tonight. I'll share some of the software, but we're supposed to be looking at the Andromeda galaxy tonight. But before I go into that, let me have Sunny introduce himself. Sunny, take a moment, please, to introduce yourself. Thank you for connecting on Zoom.
Hi, everyone. So, oh, hang on. Hi,
Yeah, we
everyone.
can hear you. Yeah. We can hear you.
So, my name is Sunny Kaniokua. And I'm a student at Akaula on the island of Molokai in Hawaii. And I was introduced to Dr. Raja here through my teachers, and just I believe it was last Friday, right? I was down at the Keck Observatory on the island of Big Island in Waimea, and it was such a fun experience. It was a learning curve for me because everything was there, and well, it's like actually being at an observatory and looking at all the tech. So thank you, Uncle Raja, for inviting me there.
Of course.
I hope that I'll be able to go back when you're there and visit sometime again.
I'm sure we'll make that happen, Sunny. And so Sunny is at the Akaula School on the island of Molokai, like you said. And I actually visited Molokai a few days ago on Thursday. Last week I was in Molokai, so we met in person. And the next day his family had come over to a different island, the Big Island of Hawai'i. And so he and his parents got to visit the exact room where I'm sitting. And in a moment, when Lara has a break, I'm working with Lara Cullinane here. She'll introduce herself. So why don't I start? Why don't I share my screen to show you what kind of data we have in mind to collect? I say we haven't collected them tonight yet because of clouds. When we are pointing the telescope right now in the direction we need to point to, we're not getting the full brightness that we expect to get from the stars because there are clouds along the way. Lara, how's the cloud situation right now? Okay, so we're not taking any spectrum. May as well let it run. May as well. We'll see what we got it. Got it. So I'm going to share my screen so you can see what we're doing here. Oh, Lara, yeah, Lara's going to introduce herself.
I'm Lara. I'm a postdoc at Johns Hopkins University, and I work very closely with Raja on this M31 project that we're studying at the moment, and I wish it was clear. Great to meet you all.
So that's Future Hope in Kolkata. Deb and Eric are in Waimea. That's who I went snorkeling with this morning. Sunny, you met, is back in Molokai, and Rob is connected from Southern California. And Shamika is connected from, All right, thanks. So I'm going to show you all a picture of the Andromeda galaxy that we're studying tonight. I have to show you old pictures because tonight's pictures are not very good because of the clouds. So please bear with me a moment and I'll share my screen. All right, I'm ready to share my screen now. You should be able to see my full screen. And if anybody wants to ask a question at any point, please stop and ask me questions. So this is this slide right here that I'm about to put on full screen is a part of the Andromeda galaxy. You can see the center of the Andromeda galaxy up here. This little galaxy down here, it's very small, is called M32. Okay, and you're looking at the disk of Andromeda. M32 is at least superposed onto the disk of Andromeda. It looks like it's close to the disk of Andromeda. Of course, it could be in front, it could be at the back, but at least when we take an image, they look like they are close to each other. And that's one of the things we're trying to determine is how close are they? And we're trying to determine that indirectly. We can't directly measure distances with enough precision. So we're trying to understand if there's any gravitational interaction between this galaxy here, M32, and this big galaxy here, M31, at least this part of that galaxy, the part of the big galaxy that appears to be close to M32. These other circles that you see here, these are bright stars. Most of them are bright stars in the Milky Way. They're in the foreground. But this we know is a small galaxy, and we know it's close to M31. We just don't know how close. Okay, I'm going to skip through the next these slides here. You can see, this is also zoomed in on M32. You can the main part of M31 is off the top of this image, and you can see, and we've tried to study this in the past. This was in 2019. We studied this region of Andromeda. Over the last few nights, and including tonight, we're trying to study the part of Andromeda that's over here. Now, this is a very strange image. This looks like you just see a bunch of colored dots, but every dot is a star in the Andromeda galaxy for which we've measured a velocity. And I should say some of the stars, instead of being in Andromeda, are part of the M32 galaxy. M32 itself has a velocity of about minus 180. The color of the dot is indicative of its velocity. So we've taken spectra of all of these stars. We've measured their velocity using the Doppler shift method. And you can see that the stars that are up here, they have velocities that are close to minus 100, between 0 and minus 100. You can see the colors are between yellow and light orange here. Most stars, not every star, but most stars have colors in that range. Whereas the colors down here are not between 0 and minus 100. Instead, they're between minus 500 and minus 600. It's almost symmetric because minus 300 is known to be the speed at which Andromeda is moving towards us. So this is as though someone has thrown a frisbee towards us. We know the overall velocity of that frisbee. We know by measuring it, we know the center of Andromeda is moving towards us at 300 kilometers per second. This part of the frisbee in the upper left is rotating in such a way that it's countering the motion of the frisbee towards us. So it's if someone throws a frisbee towards you, the frisbee is both spinning and it's traveling towards us. So the Andromeda frisbee is traveling towards us at 300 kilometers per second, very high speed, 300 kilometers per second. Think about that for a minute. That's very, very fast. But it's also spinning. So this part of it isn't moving towards us as fast as 300. It's instead moving towards us at a speed of more like minus 50. So it's rotating at 250 while Andromeda is moving towards us at 300. So the net effect of that is the rotation is almost completely countering the translational motion, the forward motion of the frisbee. On the lower right side, the rotation of the frisbee is enhancing the rotational motion. So you can see the typical speed here is like the color is light purple. So that's 550. So that's like minus 300 and minus 250 added instead of subtracted. So that side of the frisbee, the rotation is in the same direction as the motion of the frisbee towards us. So you can see this very clearly. Every one of these dots is a star whose velocity our group has measured using the instrumental setup we are using tonight, using the Keck telescope, the DEIMOS spectrograph. Exactly the setup we are using tonight is what we used to measure the velocities of these stars over years. So we started this project in 2010. This is our 14th year making these measurements. In between, we went off and studied other galaxies, but we've come back to this. Deb and Eric, this is almost like my art. I start a sketch, then I go off and do something else, and I come back to it. So this is Andromeda has been like that. We did the upper part of this galaxy in the years 2010, 11, and 12, 2010, 2011, 2012. Then we went off and studied other galaxies for a bit. And then the last few years, 2019, 2022, and 2023, we've been focusing on the lower right part of the galaxy. Before we go any further, let me see if there are any questions. I'm going to pause my screen share for a moment to see if there are any questions. And in particular, I'm very interested in seeing if the students in Future Hope School have any questions for me. And please feel free to ask. There's no question that is too basic or too complicated. I'll do my best. Okay, so please go ahead. Any students? And if you have a question, put up your hand and so someone can send the microphone to you, and feel free to ask a question.
Sir, what do you mean by that? Any question?
Yeah, any questions from any of the students? Okay.
Sir, what do you mean by velocity?
Oh, okay. Very good. It's the same as speed, but it's speed with a direction. Speed is how you know what speed is, of course, it's very common to measure speed in kilometers per hour, right? When a car is traveling down the streets of Kolkata or a bus is traveling, you measure the speed in kilometers per hour. When you specify the direction of the speed that is moving away from us or towards us or going from left to right, that combination is called velocity. Speed plus a direction. And you will study this in physics soon. The meaning of the term velocity. It's very similar to the term, to the meaning of the word speed, except it has a direction associated with it. In our case, that's a great question, by the way. That's a very, very good question. Thank you for asking. In our case, the way we are denoting the direction is by a plus and minus sign. You saw that the velocities in that picture, I'll go back to sharing it in a minute. Remember that all the velocities had negative values. Remember that? All were negative. Negative means they're moving towards us. Positive means away. Sunny, you have a question. Please go ahead.
So, is the galaxy like a propeller in which the edge of the galaxy travels faster than the center?
You know, that's a great question, Sunny. When you have a spinning frisbee or a propeller, the edge rotates faster than the center because it rotates like a solid body. Galaxies don't rotate like solid bodies. Instead, most stars move at the same speed, or same, in this case, same rotational velocity. In Andromeda, that speed is about 250 to 270 kilometers per second. They all move at roughly the same speed. So stars that are in the inner part complete a circle in a much shorter time than stars in the outer parts. In this sense, it's different from a spinning propeller or a spinning frisbee. Sunny, did that answer your question?
Yes, that did. Thank you.
Yeah. So this concept, the way a propeller rotates or a frisbee rotates, that's called solid body rotation. And you're absolutely right. In solid bodies, the outer edge rotates faster than a star near the center. But in galaxies, that's not the case because the stars are not connected to any, unlike, let's say, in a propeller, the metal, all the atoms are connected together by atomic bonds. Galaxies, the stars in galaxies are not connected like that. So it turns out that the stars near the center of the galaxy travel at about the same speed as stars near the outer edge. So the ones near the Future Hope students, you guys are excellent athletes. You know that if you're running on a circular track, the person in the outer track has to cover a larger distance to complete a circle than a person on an inner track. Right. How many of you take part in athletics in the school? Quick show of hands. I see some of you in your sports jerseys, so I know that some of you are take part in athletics. Right, but do you know what I'm talking about? If you run in a circular track, if you have a circular track, those in the inner track have to cover a shorter distance than those in the outer track. So if everyone runs at the same speed, the inner track people take a shorter amount of time to complete a circle. Does that make sense? Okay, other questions? And Future Hope, you guys asked one question already. Please see if there's any other questions in the room. There are many of you in that room. 40 of you in that room. Do you know how far away the Andromeda galaxy is? That's the one we're studying tonight. Anyone remember? I think I might have mentioned it when I visited your school, but it's fine if you don't remember. Anyone want to guess? It's measured in light years. Can anyone look it up online? How far away is the Andromeda galaxy? You could ask ChatGPT or you can look it up online. Go ahead. Anyone want to answer how far away Andromeda is? Go ahead.
What happened when two galaxies collide?
I will show you a video of what happens when two galaxies collide. Let's quickly get to the answer of how far away Andromeda is. Anyone know? Can you look it up on your phone or on a laptop? No? Let me know if you need the answer. Go ahead, Sunny.
Andromeda is 2.5 million light years away from the Milky Way galaxy.
That's exactly right. 2.5 million years of light travel time. Light travels very fast. Light travels around the Earth. Thank you, Sunny. That's great. Light travels around the Earth 7 times in 1 second. Travels so fast. Light travels at 300,000 kilometers per second. So in 1 second, it travels around the Earth 7 times. And yet Andromeda is so far away that light takes 2.5 million years to reach us. Now, there was a question there about what happens when galaxies collide. I can show you a quick video to demonstrate what that looks like. So bear with me a moment. I'll show you a quick video of what that looks like. I'm going to turn this one off for a moment. And I will go to a different PowerPoint slide to show you that. Let's see if I can find that. Now, the problem is galaxies take a very long time to collide. It takes billions of years to collide. So we can't actually watch a pair of galaxies collide in human lifetime. But what we can do is we can create computer simulations that include in them all the effects of gravity. They include realistic structures for the galaxies. So then you can see what happens. You can predict what happens when 2 galaxies come close together. So let me show you what that looks like. Okay. Can you see my screen? If someone could please, so I can't see you right now because I'm sharing my screen. Can you see my screen? What does it look like?
It's black right now.
Okay, and what is it? Do you see the text computer simulations?
Yes.
Okay, I'm going to remove the label and I'm going to play my video. So you see 2 galaxies. These are ideal galaxies. They're created on a computer. So you can see their shape. But right there, 2 galaxies right before they collide. These are 2 real galaxies that are about to collide. This is a real image of 2 galaxies. So when you go back to the computer simulation, you can see that the 2 galaxies, after a little while, they start to intersect. That is, each one is in the other one's space. And so we are changing our perspective of the simulated galaxies. And this is a real pair of galaxies that are invading each other's space. So if we go back to the computer simulation, you can see each galaxy stretches out the other one into these long tails. And this is a real pair of galaxies where one galaxy is stretching out the other and vice versa. Again, back to the computer simulation, the main bodies of the galaxies are about to collide. Right before that, we stop the computer simulation. So we can show you an example of a real pair of galaxies that have already stretched out like that, and the main bodies are about to collide. And then one more, we go back to the computer simulation. This is what happens when galaxies collide, is you go from having 2 galaxies to 1, and but you also get these very long tails of stars that are produced. This is an actual collision product, what you're seeing on the screen now. Okay. So I'll stop the computer simulation, but I just wanted to say that this is what we think happens when galaxies collide. The stars in one galaxy initially were going around a common center, and they were initially going around a common center, one galaxy. The other galaxy stars were going around its center. When they come together, they destroy each other's shapes, and you have a set of stars that are orbiting a common center. Okay. Sunny, you had your hand up. Please go ahead.
So when 2 galaxies collide with each other, what happens to the black holes at the center of both of them?
Great question. At the end of near the late stages of the collision, when the black holes have the centers, so you saw that the main body of the galaxy takes a little while for the 2 of them to merge. When they finally do, we think the black holes at their centers ultimately merge and form a bigger black hole. Bigger, more massive.
Okay, thank you.
Sure, of course. And Sunny, remind me, you're junior in high school now, right? You're in class 11, grade 11?
Yes, I am.
Okay. That's a great question. Any questions from Jamaica, from you, Rob, Eric, Deb, anything about the format of what we're doing? You know, we would normally be sharing the instrument controls, and I'll do that in a minute because we have the instrument controls on, even though skies are cloudy, we're still trying to take data. So I will show that. So while I'm getting that set up to show you, if the Future Hope students have any questions for me, please feel free to ask. Okay. Any questions from the Future Hope students?
How much time it's take to collapse two galaxies?
Please just give me one moment. I'm going to ask you to repeat your question. I didn't hear you very well. Could you ask your question one more time, please?
How many times it's take to collapse two galaxies?
Oh, okay. How long does it take for two galaxies to collide? I'll give you a number. It is between 2 and 5 billion years. Okay, so not a billion has 9 zeros. So it takes a very long time. A few billion years would be a typical number. It depends. It depends a little bit on how massive the two galaxies are, how close they get, you know, whether they're on a direct collision or if they're on a grazing path. It depends on those things. The galaxies basically first start going around each other, and then they get into a tighter and tighter spiral. The outer parts get flung away, and the inner parts collide. So there's not a simple answer to your question. It really depends on the properties of the galaxies and what kind of orbit they're in relative to each other. Yeah, so it's a great question. It's a very, very good question. And just to give you an idea, our sun, which has a solar system of planets around it, is going around the center of our Milky Way. And it goes around 5 times in 1 billion years. So it takes 1/5 of a billion years, so 200 million years, to go around the center of our galaxy once. Okay. Okay, someone else was going to ask a question. I saw that someone else came up to the microphone, so please go ahead. And I know that it is, is it 12 o'clock in Kolkata right now, 12:05? And you said your lunch break is until 1:10 or starts at 1:10?
Yes.
Starts at 1:10.
Starts at
Lunch what are start?
1:10.
Lunch quarter 1:10. You know,
No, sir.
so
1:10.
I heard you saying in Bengali. I can speak Bangla too. 1:10, okay. Lunch একটা 10-এ শুরু হয়।
হ্যাঁ।
Rob and Deb, Eric, Jamaica and Sunny, you get to hear me practice my Bengali. Oh, thank you. Thank you for taking a picture of the group. Please send it to me. We'll post it on our site. I ate lunch, Anand and I ate lunch at your cafeteria when we came there a month ago. You have a wonderful school and a wonderful kitchen. Yeah. All right. Other questions? Other questions, please. And then I'll go back to sharing my screen. Go ahead. I see someone waving from the back. Did you want to ask a question, young man?
I want to ask, is sun is the in the solar system, why there is no light in the space?
You know, that's a good question. That's a very good question. There is light in space. It's not that there is no light in space. In fact, there is light at It's the light of the stars at night. It's not as much light as the daytime sky because we happen to be very close to our own sun. Okay, and I'll give you some measure of that. The typical distance between stars in the Milky Way, say in our part of the Milky Way, the typical distance between stars is about 4, 5, maybe 10 years of light travel time. 4 light years is the distance to the nearest star to the sun, but a more typical distance might be 10 light years. 10 light years, that's a typical distance between stars. So if you put yourself in an average part of our Milky Way, you might find that the nearest star is roughly 5 or 10 light years away. Do you know how close we are to our sun? How many light years is the Earth from the sun? Does anyone know? This is a good question for Future Hope. How long does light take to travel from the sun to the Earth? How many years or any units? How many hours, days?
Sir, 5 billion, 30 million.
No, it doesn't take that long. The sun is very close to the Earth. It only takes 5 light from the sun only takes 500 seconds to reach the Earth, 8 minutes, little over 8 minutes to reach the Earth. So that's how close we are to our sun. That's why the sun looks so bright during the day. If you were 10 light years away from the sun or 5 light years away from the sun would look like most other stars in the sky. It wouldn't look very bright. The space would indeed be very dark. Sunny, go ahead.
So
Question.
if the sun were to blow up, we wouldn't notice it until 8 minutes after?
That's correct. Anything but the sun does, we only experience it 8 minutes later or 500 seconds later.
Okay, thank you.
Sure. Does that answer your question about why space is so dark? It's because compared to daytime, say on Earth, right? That's the implication I took from your question. It's just that during the daytime, we get to see the sun, which is very, very close to the Earth, compared to the typical distance between stars in space. Typical distance between stars in space inside our Milky Way, say. Does that answer your question? And Sunny, please go ahead. Please go ahead. You can speak up. You don't need to. We are a small group. You can always speak up.
Okay, so
don't need to raise your hand.
Does the universe expand faster than the matter that fills it?
What do you mean by the matter that faster than the matter that fills it? I don't think I understand your question.
I believe it was last year during our astronomy class, we learned about dark energy and dark matter, which of course are theoretical. And what we learned is that dark energy sort of expands the universe while dark matter fills it. So my question is, does that dark energy expand faster than it takes dark matter to fill it?
So I'm going to correct that a little bit. It's not fair to say that dark matter and dark energy, that one fills it and one expands it. They both fill space. Both of them do. But the effect of dark energy is to push things apart, is to try to make space expand. And the effect of dark matter is to pull things closer together. So one has the effect of pushing things out, like an outward pressure pushes galaxies apart from each other. That's what dark energy does. Dark matter tends to pull galaxies close together. So they both fill space, but of course, as the universe expands, or depends on which one is winning, the universe will either expand or contract. And we live in a universe where dark energy, the thing that pushes things apart, is winning compared to the thing that pulls things together. And it really has to do with how much of it there is. In a rough percentage, about 25 to 30% of all matter, of all the stuff in the universe is of the kind that attracts, and 70% is of the kind that push apart. So dark energy makes up about 70% of the universe in terms of the budget, the energy budget of the universe. So we're talking about, yeah, so thank you, Sonny. And we're talking about something very abstract, dark matter and dark energy, but I should make another statement here, is they are not just theories. There's direct evidence for the existence of dark matter. The most obvious example of that is the speed at which galaxies spin can't be explained by the gravity of the material that we see. So there has to be, unseen matter whose gravity is causing galaxies to spin as fast as they do. If they just had the stars we see, galaxies would be spinning much more slowly than we observe them to. In this sense, there's empirical evidence that galaxies contain some kind of unseen matter, and that's what dark matter is. Similarly, there is direct empirical evidence that the universe's expansion is speeding up over time, which indicates that there's some agent that is pushing galaxies apart faster, and it's countering the effects of dark matter, winning over dark matter. Empirical evidence for both of these things, dark matter and dark energy. Even though we don't understand their detailed microscopic nature.
Okay, thank you for clarifying.
Of course. This is great. I know you were doing a space module in school last year. What subjects for Future Hope in class 6? What subjects are you studying? What classes are you studying in school today? What subject? English, Bengali, Hindi? Okay. Yeah, go ahead. Tell me which classes you're studying.
Hello, sir. My name is Alekat. I'm from 6. My question is, how is black hole formed?
I will explain. I will do my best to answer how a black hole is formed. What we know so far, it's a question to which we don't know the complete answer. We know that if a star, the sun is a star, but there are stars that are much more massive than the sun. And if those stars are stars that are more than about 5 times the mass of the sun, at the end of their lives, when they run out of fuel, they collapse, the central parts collapse to form a black hole. That's one thing we sort of understand in terms of formation of black holes. We also think that black holes can get more massive by merging with other black holes. Like Sunny asked what happens when galaxies collide, the black holes at their centers merge. But I would say that there are a lot of unanswered questions about the formation of black holes and how they grow from small black holes to bigger black holes. So it's a great question. Thank you for asking that. We don't fully understand the formation of black holes. There was a very famous Indian scientist who predicted many years ago that if a star is more massive than a certain value, 1.44 times the mass of the sun, if a star is more than, let's say, 1.5 times the mass of the sun, that it cannot hold itself up against its own gravity. It cannot become something called a white dwarf star. We know the sun will become a white dwarf star, but this very famous Indian astrophysicist, his name is Subramanian Chandrasekhar, he showed that stars that are more massive than a certain limit, 1.44 times the mass of the sun, cannot end their lives as white dwarfs and must collapse. We now know that stars do collapse and they form either neutron stars or black holes, depending on how massive they are. If they're just above 1.5, if they're 2, 2.5, they form neutron stars. But if they're 5 or 10, they form black holes. If that's 5 or 10 times the mass of the sun. Okay. Does that answer your question a little bit? Yeah. Okay. This is something you will study if you study physics at school. What subjects are you studying right now in class 6? कौन-कौन सा
English, maths, Bengali, third language, science, social science.
What is your third language? Are you studying Hindi as your third language?
Yes, sir.
And Bengali is your second language that you're studying. And social science and science. Okay. So in science, there's physics, chemistry, and math and biology. And what I've just described to you is part of physics. Okay. And I know right now you're studying it as science, but when you go to class 9 and 10, you'll study the separate subjects of, I think, in class, how about class 8? Do you study, what subjects are the class 8 students studying? Same thing?
Good morning. My name is Irshad Ahmed. I'm from class 8.
Louder.
Good
Yeah,
morning.
we can hear you. Yeah.
My name is Irshad Ahmed.
Yeah,
I'm from
I can
class
hear
8.
you. Yeah, Rishad, we can hear you. Go ahead. Yeah.
Science, Hindi, English, a third language as Hindi, SST, Science, English. That's all we study.
What is your third language? Which is your third?
Bengali.
Okay. Do you know what subjects you study in class 9?
Roger, can you repeat your question? It was a bit garbled.
Sorry about that. Do you know what subjects you get to study in class 9, in grade 9?
English.
Okay. What other subjects in class 9?
Science, physics, chemistry, biology.
Physics, chemistry, and biology separately in class 9 then. Okay. Yeah. How black holes form from stars is something I never learned in school, and it may not be part of your school and exam curriculum, but it's something that if you were interested in, you could study outside of school, but you can also, this is something that college students might study. Okay. Thank you for asking that. Those are great questions. Okay, I promised to share my screen. Let me do that. Oh, and Lara, by the way, I've been copying data over to my server in Santa Cruz. Night 1 is all copied. Night 2 is in the process of copying. Of course, I'll have to do that 2-step copy for night 3, first copy to my laptop. So right now I'm copying from my laptop to my server. And so that's going fine. It copied the first 75 files from night 1. And 2, we have, of course, the calibrations take up a lot of the space, but so it's not exactly double the data volume. Okay.
Sir,
Yes, please go ahead.
did the size of black hole increase?
Yeah. So the sizes of black holes in general do increase over time because, and let me explain what the size of a black hole even means. Because a black hole can trap light over a certain region of space. It's able to capture light over a certain region of space. And as the black hole gets more and more massive, that region of space over which it can trap light gets bigger and bigger. And it's a direct proportionality. If you make a black hole, if you have 2 black holes, one is double the mass of the other, then the radius of the region within which the more massive black hole can trap light, that radius is double the radius for the smaller black hole, of the radius of the region over which the smaller black hole can trap light. So this radius is sometimes called the Schwarzschild radius. I'm going to put this name in the chat. It's called the Schwarzschild radius. It's named after the German scientist who first worked out the mathematics of Einstein's, who first, I don't know if you can hear me. This is there was a German scientist named Karl Schwarzschild, who was the first to work out the mathematics and physics of Einstein's relativity. So the radius of influence of a black hole is called its. By the way, Can the Future Hope students see what I'm typing into the chat? It should show up in the chat window of the laptop that's being used to run Zoom. This you may need one of your
Yes,
teachers'
we
help.
can see the chat.
You can see the chat. Oh, good, good, excellent. So the radius radius of the region, the spherical region, I should say. I'm typing this in because I want you to see it precisely. The radius of the spherical region over which a black hole traps light is known as the Schwarzschild radius. And the Schwarzschild radius of a black hole is directly proportional. Do the students know what directly proportional means? Directly proportional. Have you studied this in mathematics, what direct proportionality means? Okay, I wanted to type those couple of sentences into the chat. Can someone please read it out for those? Can everyone see the chat on the screen at Future Hope? Would you like someone to read it out for you? Yeah, please go ahead, read it out. Don't eat your pen. Or pencil.
Radius of the spherical regions over which a black hole traps light is known as the
Schwarzschild radius.
The Schwarzschild radius of the black hole is directly proportional to its mass.
What that means is if you have two black holes, one's mass is 10 times that of the other, the radius of influence of the more massive black hole is 10 times the radius of influence of the less massive black hole. If it's 5 times, then the radius is 5 times. So the radius of influence is proportional to the mass. And that is something that Carl Schwarzschild worked out by solving Einstein's equations of general relativity. Einstein came up with a theory of gravity called general relativity. I'll type that name into the chat. I had the good fortune of knowing Carl Schwarzschild's son, Martin Schwarzschild. He was a professor of mine, and I learned a lot of things from him, including hearing stories about his father and hearing stories about Albert Einstein, who worked very closely with his father. So I feel very lucky to have had that opportunity. This was going on, Carl Schwarzschild's work, Einstein's work, this was going on about 100 years ago.
Hello, sir.
Yes. Hello.
My name is Ajay Yadav.
Hi, sir.
I have a question. What is
please.
inside the black hole?
That's a great question. It's not something we can answer very easily. All we can sense from the outside of a black hole is we can only answer 3 questions about the inside of a black hole. And this is a very famous theorem that was coined by John Wheeler. I'm going to put the name in the chat. John Wheeler came up with a theorem. John Wheeler's theorem was called, it had a cute name. I'm going to write this in the chat. A black hole has no hair. This was John Wheeler's theorem, and it's, in a way, it answers your question. From the outside of a black hole, outside the Schwarzschild radius of a black hole, we can measure 3 things about a black hole. We can measure how massive it is. We can measure how much charge it contains, positive charge or negative charge, the net charge, and we can measure the spin of the black hole. But we can't say that inside it's made up of carbon or made up of carbon dioxide, made up of water. There's no, all information about its chemistry is lost to someone who's observing the black hole from the outside. So Sanjay, that was a very good question, and it's got an extremely deep answer, not a simple answer at all. It seems like in your class, there's a huge amount of interest about black holes. Am I right? Because many of your questions have been about black holes, and this is indeed a subject that is at the heart of one of the main subjects that astrophysics, matter, dark energy, black holes. Yeah, go ahead. Go ahead. Another question.
Hi, sir. My name is Ryan Sharma. I'm from class 6. My question is, what if we go inside the black hole?
If a person were to fall into a black hole, long before they went past the Schwarzschild radius beyond which they couldn't communicate or send light out, long before that, they would get stretched to the point where they would die. They would get stretched because, let's say you were falling in feet first, okay? What would happen is your feet are being pulled harder, would be pulled harder than your head because your feet are closer to the black hole. And gravity depends on distance. So the black hole would pull on your feet harder than your head. That would stretch out someone. And it's called spaghettification. People would turn into, anything you drop in would sort of turn into a long string like noodles or spaghetti. That's the short answer. Is it's a very, it would be a violent and instant death. So we have an announcement coming in just a moment. For the folks on Zoom, the good news is the skies are clearing. We're starting to get good data here. Now, are you all having fun? The folks in Future Hope. What class are you missing by joining this Zoom call? What would you be doing normally at this time? Yeah, what is this time slot?
Maths.
Maths? Okay. So I'm glad we're talking a little bit about maths here. How many of you remember me from my visit 1 month ago? Can I have a quick show of hands? Okay. Very good. Thank you. Thank you. We talked about some maths when I visited your classroom. Okay. I feel a little guilty that you're missing maths class, so I feel compelled to tell you something about maths. Yeah. Okay. Can someone tell me what the square of the number 4 is? What is the square of the number 4? What is 4 multiplied by 4? Anyone, whoever has the microphone.
4 months.
No, 4 multiplied by 4. What is 4 multiplied by 4?
4 square.
Yeah, but what is the number? What is 4 squared?
16.
16, okay. What is 5 squared?
16 square.
25, okay. 5 squared is 25, 4 squared is 16. What is the difference between 25 and 16? If you subtract one from the other, what do you get? What is 25 minus 16? You said 5 squared is 25, 4 squared is 16. What is the difference between them?
What was that?
Difference between 25 and 16. Subtract 25, subtract 16 from 25. What do you get? Someone shouted it up. I think I heard it. 9, right? 9. What were the two numbers we used? 5 and 4, right? 9, right? So we used 5 and 4. 5 squared was 25. 4 squared was 16. We took the difference and we got 9. Notice that 9 is equal to 5 plus 4. This works for any successive pairs of numbers. What is 11 squared?
21.
121.
No, 11.
11 squared. 121, right? What is 10 squared?
121.
What is 10 squared?
100.
100. So what is the difference between them? 121 and 100. If you subtract 100 from 121, what do you get?
21.
You notice that is equal to 10 plus 11.
21 is 10
10 plus 11 whole.
Uh,
21 is 10 plus 11 whole. 21 is 10 plus 11 whole.
So this works for any pair of numbers, any pair of successive numbers. You can try this for 3 and 4 and tell me if it works. What is 3 squared?
9. 9.
What is 4 squared?
16.
What's the difference?
16 and 9.
Between 16 minus 9?
9 minus 16.
7.
7.
7. Is that equal to 3 plus 4? It even works for 0 and 1. What is 0 squared?
0.
And what is 1 squared?
1.
What is their difference?
0 and 1.
1 is equal to 0 plus 1, which is equal to 0 plus 1. Yeah, it works for any pair of numbers. Now, if you really think about it, as you get a little older, when you get beyond class 8, ask your older fellow students, those in class 9 or 10, those who are studying algebra, ask them why, whether they can explain to you why this is the case. Why is it that when you take one number, square it, and you take the next one less than it and square it, the difference is equal to the sum of the two original numbers. You can ask them, and they'll maybe they can use algebra to explain why it works like that. Okay. All right. We should go and look at what our screen is doing, what kind of data we're collecting. Let me see how I can do that. Let me just check on that. Give me a moment, please. I'm a little worried that if I share my screen with VNC, it will kill my copying that I'm doing, because I have to have the VPN running for that. Right. So let me see how else. Okay, I can show some other data that were collected recently, not just now, but just very similar to the data we're collecting tonight. Yeah, let me show that. That would be a good way to. Okay, I'm going to share my screen. Okay, so all of you can see this screen, this one. Let me minimize this thing here. What you're looking at on this screen here, where my cursor is, these horizontal lines, black lines against a light gray or white background. These are spectra of stars in the Andromeda galaxy that we collected recently. So every horizontal black line is a different star. And if you look very closely, there is a bright one in the middle where my cursor is. Above it, there's one that's a little less bright, but below it, there's a faint one. Below the original one, there's a faint one. And above there's 1, 2, 3, 4 horizontal streaks of light. Can you see that? It's in fact, if I'm not mistaken, there are 5 streaks. One where my cursor is, if you can see my cursor. I'm going to zoom in, actually. I'm going to zoom in a long way. It takes a little while to zoom. That's why it's going. Let's see. So the question is, you can see below it, you can see a very faint streak. That's the light of a second star. So 1, 2, 3, 4, 5. There are 5 different stars whose light is landing within the slit. Some of them are bright, some of them are faint. Some of them are sending all of their light into this rectangular cut, a slit. Some of them are we're only capturing a portion of the light of the star because the star is not in the center of the slit, it's off the center. Okay, so there are 5 stars here whose light we can capture. We can measure for each of these, we can measure how bright how much light is coming in at every color or every wavelength. So you've all seen a rainbow. In Bengali, that's called a Ramdhanu, right? Which is, you see the different colors of white light. What are the colors in the rainbow? Anyone know me? What are the colors in the rainbow? How many colors are in the rainbow? How many colors? Have you guys studied a rainbow in school and Future Hope? Go ahead. Any one of you can answer. How many colors in the rainbow? No one? Have you heard of VIB? Have you heard of this? These are the colors. Please tell me if you've studied this in school. These are the colors of the rainbow. Have you studied this in school, Future Hope? Class 6 or class 8?
Yes.
You have studied it, okay. You can, of course, I'm sure many of you have seen a rainbow on a rainy day when sunlight is hitting raindrops. You can get the colors of the rainbow. In our instrument, we take the light from stars in Andromeda and we break it up into thousands of colors, not 7, but thousands of colors. In our case, more than 8,000 colors. And for every color, we can see how much light we're receiving. That is what this graph is. The y-axis of the graph, the vertical axis of the graph is telling us the taller it is. That means the more light there is at that wavelength. And the x-axis, the horizontal axis, is telling us the color of the light. But it's a funny way to measure a color using numbers. Instead of names like violet, indigo, blue, green, yellow, orange, red, we use numbers to measure the color of light. And that's the x-axis. The y-axis is measuring how much light there is at every wavelength or every color. Okay, so I did want to share this with you. This is something called a 2-dimensional spectrum. This is what we were looking at before. And from that, we make something called a 1-dimensional spectrum. Let's see, what else can I show you here? In this window over here, you can see that these numbers are changing. I'm copying the data we collected on Saturday night from my laptop. We first copied it from the computer that controls the telescope. We copied it from there onto my laptop. And now, right now, this copying that you see going on here, 43, 44, 46%, this is copying it from my laptop to a computer in California, a big computer in California, that we will use to do the processing of the data. We have to do some analysis of the data that will happen on a computer in California. Okay. You can see that the numbers are sequential. D is for DEIMOS, which is the name of the spectrograph we're using. 10 is the month, it's October. 08 is the date on which we collected the data. Today is, of course, 10th October right now in India. but when we collected it was 2 days ago, 08. And this is the number of the file. 0031 is the 31st file. 0043 is the 43rd file. We're copying them one by one. And you can see this percentage keeps increasing slowly, but surely it keeps increasing. It's at 32% now, but it will go up in a bit. It will go up to for some reason it's really slowed down temporarily, hopefully. Yeah, you can see the percentages going up again. It had sometimes it's that percentage is going up rapidly, sometimes it's just stalled. So one of the really nice things about stars is when you take a spectrum like this, I'm going to zoom in. And you should one over there, that are marked by these dotted lines. So from this, we can measure the velocity of the star, and we can see that the star is traveling towards us at 327.7 kilometers per second. Again, we for this experiment, we use units of kilometers per second. And these 3 dips are produced by the element calcium, which is the 20th element in the periodic table, produced by calcium, inside the calcium that is present in the outer layers of the stars in Andromeda. You can actually measure the amount of calcium, but in this case, we're measuring how fast the star is moving by using these dips produced by calcium. Let me stop sharing for a moment so I can see all your faces. And oh, that's a very good point, Rob. Indeed, in this sense, small black holes are more dangerous than massive black holes. Yeah. It really depends on the amount of shear, as you said, exactly what the tidal force is. And in fact, the curvature of the event horizon gets lower and lower the more massive the black hole, because the radius of curvature increases in proportion to the mass. I haven't thought about whether it would be survivable, though. Thank you, Rob. That's a great point. Any questions about the spectra you just saw? Anything that you've seen? I know we are. It is. I hope you're not missing lunch at Future Hope. You're sure that lunch starts at 1:10? Yes.
Sir, my question is how rainbow formed?
Oh, that's a very good question. How does a rainbow form? Have you used a prism, glass prism in school, like a triangular piece of glass?
No, sir.
No? No, okay. So if you, the reason you get a rainbow is because light of different colors, first of all, white light is made up of different colors: violet, indigo, blue, green, yellow, orange, red. Is a sort of rough way to describe the colors that make up white light. These different colors of light travel at different speeds when they're traveling through glass or water or any other transparent medium. The differences are very slight when they're traveling through air. In vacuum, in the absence of air, these different colors travel at exactly the same speed, but they travel at slightly different speeds inside glass or water, any transparent medium. Can you guess which of those travels fastest and which one the slowest? Of violet, indigo, blue, green, yellow, orange, red? Which one of those travels fastest? Which one the slowest? Any guesses?
White.
Well, white is the composition of all of them, but when it's traveling through a medium like, what's the, am I even making any light travels at different speeds in different kinds of transparent media. So in glass, it travels more slowly than it does in air. In air, it travels slightly more slowly than it does in vacuum. But when you have a surface where light is going from one speed to a different speed, let's say from air to glass or from air to water, light bends, and different colors of light bend by different amounts. Violet bends the most, red bends the least of the 7 colors in the rainbow. And because they bend by different amounts, that splits up the light into its colors. That's how you form the detailed formation of a rainbow is actually quite complicated. It involves something called total internal reflection. It involves reflection, not just bending of light, but also reflection. And gets this separation of the colors of white light. Sorry, I wasn't able to answer your question very well, but it's actually quite complicated to understand exactly how a rainbow forms. But I think the simple thing to remember is when light travels from one transparent medium to another, it bends at that interface, and the amount of bending is different for different colors of light, and that's related to how you form a rainbow. It's not the complete reason for it, but it's related to it. How long does it take to compile the data or to reduce the data? Jamaica, it's a matter of hours, for each mask, because we observe the data in the form of these multi-slit masks. So for each set of the 200 stars, it takes a few hours. And this, the compilation, the actual copying, that is not that long. A night's worth of data might be copied over in 1 hour. It just depends on what the bandwidth is available at any given time. I'm doing it's a 2-step process. I first download it from a computer on the mountaintop to my laptop. The reason it can't be a one-step process is because of various firewall issues, security issues for the different computers. The Keck computer and the UC computers are set up such that they don't talk directly to each other. I can tunnel into the firewall of one, copy it into my laptop, and then I can tunnel into the firewall of the other and copy it from my laptop to the one in California. But those I can't tunnel at the same time. Yes. Right. How am I doing in terms of answering questions? Are the folks in your classroom there in Future Hope? Are there still 40 students in class, or have some people left? Still about 40 people in the class, in the room. What room are you in? Is that the library?
Yes.
Okay. And are there still 40 students in the room? I can't see everyone, so I can't quite tell.
Yes.
Okay.
Yes.
What's the next question that one of you might have? Go ahead.
Sir, my name is Irshad Ahmed. I wanted to ask you some questions.
Yes, please.
What is space station?
Irshad. The space station is it's like a rocket. It's a capsule that is in orbit around the Earth. Okay, it takes 90 days. Sorry, it takes 90 minutes, not 90 days, 90 minutes to complete one full orbit around the Earth. So it's almost like a home for astronauts. If you go up in a rocket, you can get off that rocket and go into the space station, and you can be in an enclosed place, but that you're still in orbit around the Earth. So you're complete weightlessness. You experience complete weightlessness there. The space station if the one I'm thinking about, that's called the International Space Station. It was actually set up as a collaboration between different countries. NASA played a role in that. Collaborated with Americans and other countries. Canada has been involved in that. Other countries have been involved. Does that answer your question of what a space station is? Yeah.
Yes, sir. Thank you.
Thanks. Sure.
Sir, I have a question.
I want to see if anyone else in the call. Yeah, please go ahead. Go ahead.
Does the black hole move?
Yes, black holes do move. They can move in various ways. In general, just like our sun is in an orbit around the center of the Milky Way, there are black holes that are also in orbit around the center of the Milky Way. There are black holes, another, there's a massive star that's orbiting a binary. In fact, in a few hours, second half of tonight, we'll be studying these X-ray, these binaries in Andromeda. Yeah, that's a great question, Jamika. Is there an astronomy club at Future Hope? Is there a telescope at the school?
Thank you, sir. No.
Thank you. Is there a telescope at Future Hope? No? Okay. And Jamika, one of the problems in Kolkata is the light pollution and air pollution is such that it would be not very effective to use a telescope. At least that's how it was when I was growing up. And now there's a telescope associated with my college. The air is clear. Yeah.
Sir, I have a request, sir.
Yes, please.
Sir, previous year you showed us a painting of Durga that you have drawn. Sir, can you please show us again, because there are some new students.
Of course, I can do that. I have two paintings of Durga. I have a painting and a drawing, actually. Scientist to shadowing the artist. Oh yeah, Jamika is asking an excellent question. How many of you watched the Chandrayaan-3 landing, moon landing? Did all of you watch that on TV? This happened in August, right? August 23rd was the Chandrayaan landing, right?
Yes.
You all watched it?
Yes, sir.
In school? Wow.
Yes. No.
It was happening? Was it happening in the afternoon?
In home.
At home? Okay, at home. All right. I would share my screen and show two drawings of Durga. I'll start with one that I don't think I showed you, and then I'll show you the one that I think I did show. Am I sharing my screen? Not yet. I'm going to share my screen. So this is an abstract and sort of stylized version of Durga. Can you see it? Can all of you see this? You can.
We
Okay.
can see.
Okay. Can you count how many arms she has? How many hands and arms? You can't see her hands, but you can see her arms. How many does she have on each side? Right. She has one arm here, 2, 3, 4, 5 on this side as well. Can you tell what this animal is over here? It's a lion. Okay. Do you know what animal this is over here with the horns?
Yes.
This is Lara, who's that called? Huh?
Bull,
Oh, okay. This is the Mahish of Mahishashur. This is the head of a bull. Anyway, this is one drawing of Durga. I think you mean a different drawing. So let me go to the other one. That one. Did you mean a pencil drawing or a painting for the student who asked? I think you might mean this one. Is this the one you meant? There's a Durga here. Is this the drawing you wanted me to show?
Yeah. Yes.
Do you know who the person is in the picture?
Yes. The
Who is
mother.
that? My mother. Very good. Very good. Yeah. And I'll zoom in so you can see the details. So these, I've copied my mother's drawing of Durga. So she painted this Durga down here. Where is it? Right over here in the lower part. And I copied a painting. And do you know what this character is in the upper left? Who's this in the upper left? Ganesh. So that's Durga's son. It's got an elephant head. So if we zoom in, you'll see the pattern of Durga's, you can see Ganesha's sort of ornaments, the patterns here. Zoom in one more time. You can see his ornaments, his crown, his necklace. But then look at what happens to the patterns over here. They become part of my mother's face. These patterns here are part of her face. I use that for shading. Can you see that? There's a floral pattern right here. There's a fish pattern right there. But if you zoom out, you can't see the patterns. If you zoom in, you can see the patterns. Look at the patterns on her hand. It looks like mehendi, but it's really patterns that I've used to do shading. Instead of using words to do shading, I've used patterns. And so this is, I think this is the drawing you mean. This is now zoomed out completely so you can see the whole drawing. Good. Anything else you wanted to see that while I'm sharing my screen? Any other drawings?
Sir, how much time did you get to draw?
So in total, from the beginning to end, it took me 2.5 years. But I wasn't drawing every day. I wasn't drawing every week. There were certain months that went by when I didn't draw. Maybe 40
Sir,
or more than that, maybe 50 or 60 hours.
Sir, have you drawn any new drawing?
I have done one, but not since I traveled to your school. Let me show you this one. This one I had finished it just before I traveled to India and visited your school. Let me see if I can find it. This one. This was one that I finished just before I went to your school. I finished it in August and I traveled to your school in September. You saw this, right? I think I showed this in school. I'm showing you some of the details of her eyes and hair, teeth, eyebrow, hair, hairband. Did I show this to you in school? I was there.
Yes, boy. Yes, sir.
I did show this, right? So this is, I haven't finished anything else since then because I've been traveling and been busy with work. So I haven't finished anything. I've been working on another piece, but I haven't finished it yet.
Your drawing is very nice, sir.
Thank you. Thank you very much. That's very good. I think
It's
I may have
lovely.
shown. Thank you. Thank you very much. You may have seen this also. This is one of 2 cats. But this one is made up of words. you zoom in, you can see it's made up of lots of words. It's hard to read the words because it's written in calligraphy style.
Hello, sir. How many?
Please repeat your question. You got cut off. The sound cut out for me. What was your question? I just heard how many, and then I didn't hear the rest of the question.
Sir, how many days it took to complete the drawing?
Which one?
Sir, the
drawing?
Durga Ma one.
Yeah, so I started it on in January 2016 and finished in September 2018, so 2.5 years. But the number of actual days in which I drove was probably I don't know, 40 or 50 days, about an hour a day, sometimes a little more than an hour a day. But those 40 or 50 days were spread out over 2.5 years because most days I don't get to draw at all. How many days are in 2.5 years? 365 plus 365 plus 183. How much is that? It's about 900 days. So on average, every 2 weeks, every 14 days, I might have drawn one day, something like that. 1 or 2 days sometimes. Jamika, I missed the question. The question you asked about Luca, what context was that?
Oh, just I wasn't quite sure what word you were actually saying. Could you spell it in the chat?
What was the context? I've forgotten already.
Oh, you were showing the first picture, the
the goddess is Durga.
Yes, thank you.
And she's sort of the mother goddess. It's a big festival in the part of India where Future Hope is located, part of India where I grew up. And her son, the elephant-headed god, is Ganesha, or Ganesh without the A at the end. In Bengal, it's pronounced Ganesh. Durga is the worship of Durga, the festival associated with that happens around now, right? When is Durga Puja this year?
Just 6 days are left.
Oh, 6 days coming up. Okay, in 6 days. You'll have holidays from school then?
Yes, sir.
For how many days? How long are your Puja holidays? Durga Puja holidays? How many days are you off from school? Yeah, see, you sort of, that's a great question, because I will have the students answer. So what happens during the holiday? What are you going to do during the holiday? Will you go and visit various... You'll get new clothes. Okay, okay. Get new clothes. You go visit... You go visit relatives?
We will do pandal hopping.
Panel hopping. Okay, so a panel is something where they put up images. Actually, sorry, not sculpture, not images, sculpture of the goddess Durga and her 4 children. The lion that you saw there. There's a whole sort of pantheon of gods and around Durga. And so there's a huge celebration of that. And it's almost like an art festival. Different groups create these different sculptures. They're beautiful. They often will have contemporary themes. My sister's written a whole book about, her book is called In the Name of the Goddess. It's about how that's become a channel for artistic expression. My sister's an art historian in Kolkata. I'll share the book with you sometime. I can probably point it to you on Amazon or something. The name of the I'll put the name in the chat actually. So this is a book called In the Name of the Goddess, and my sister's name, the author is yeah, let me know if you find a link online. I can share that on the screen just to it's got a beautiful image on the cover of the of Durga. So my sister was a 10-year project to go around talking to the various artisans, taking pictures, of course, but also just how sort of contemporary world events, contemporary cultures have gotten incorporated into this. Oh, great. Thank you so much, Jamika. I'm going to share my screen with the group here. There we go. That's beautiful. Okay. Let me see if I can share my screen. Okay. So this is my sister's book over here. See if I can find any other images. There should be another image on the back. Oh, this is the front cover. I guess the cover doesn't show her face. It just shows the arms or the hands. There you go. And each hand is carrying a different weapon. I mean, she's meant to be the protector. So the gods have equipped her with 10 weapons, one for each of her 10 hands, 10 arms and 10 hands. So this is not seeing anything else here that would show the image. Well, this was my, yeah, there you go. 2002 to 2012. She worked for 10 years. Yeah, In the Name of the Goddess is part of the title. That's not the full title. This is the rest of it. Puja means worship. Durga is the name of the goddess. And Kolkata, of course, the name of the city. So my sister led a group that put in a proposal to turn it into a UNESCO Heritage Festival. So that was approved last year. So there was a lot of celebration in Kolkata because the festival that completely defines the city has now been recognized by UNESCO as a World Heritage Festival. UNESCO has these World Heritage buildings and sites, but they also have impermanent things. Let me stop sharing. Are the children at Future Hope excited about the Cricket World Cup that's going on right now? Yes? Are you watching that on TV from time to time? Do you know what match is coming up on October 14th on Saturday? I bet you know what match is coming up on Saturday. Are you following the Cricket World Cup? And do you know what match is coming up on Saturday the 14th?
India, Pakistan.
Very good, very good. India and Pakistan are going to play on Saturday the 14th.
And sir, it is the day of Mahalaya.
Oh, it's the day of Mahalaya, which is the first day of Durga Puja. 10 days, right? Because that's the and it's meant to be symbolic of a woman returning from her husband's home to her parents' home. Her husband's home is in this case is in
cricket.
So in this case, Durga lives in heaven with her husband, and when she returns to earth, it's like a woman returning to her parents' house, and she comes home for 10 days, and each of those 10 days is celebrated. And Mahalaya is the first of those days. Each day has a name. Wow, we've covered a lot today. We talked about astronomy, clouds, art, religion. Rob, Sunny, Eric, Deb, Jamaica, anything you guys have done? Eric, this is your first time experiencing Shadow the Scientist. Today was a somewhat unusual session in that we had one schoolroom connected. Sometimes we'll have multiple schoolrooms, sometimes we'll have only individuals. One of the teachers at Future Hope, are you going to say something? I see a microphone in your hand.
Hello, sir.
Hello.
Actually, this is the time of their lunch now.
Of
So
course,
1:10, as we said before. So
course.
can they leave now?
Of course. Absolutely.
Okay. Thank you, sir. Thank you so much.
See them again. We have other sessions coming up later in this month. Thank you very much, Future Hope. Thank you so much for joining. Really enjoyed having you there. All right. Bye.
Thank you,
Thank
sir.
you, sir. Thank you, sir.
Have a nice day,
Thank you.
sir.
Thank you.
Sir, we like the session.
Thank you. Thank you. Please keep coming back. Oh, that's wonderful. Oh, they were a bundle of energy. They always are. Every time Future Hope connects, they're amazing.
That's always fun.
So
Good for
I
you,
never-
Professor Raja. I think they were adorable and you were excellent.
Yeah, it was very
Aw,
nice
thank
to see
you,
them.
thank you.
Absolutely.
So this is it's a school that's in a part of Calcutta that's close to where I grew up. But like I said, they started a couple of years, 3 years after I left Calcutta. So this last month was my first time visiting them. I only became aware of their existence a year ago. And again, I got connected to someone who's the founder of the school. At that point, she had been running it for 37 years. It's been 38 now. And on 5 successive days, we were on the Keck telescope, 5 successive nights here. It was daytime for them. They connected, and it was Monday through Friday. And then on Friday, they said, we're really sorry, but weekends, they don't come to school. They go home, and at home, they don't have internet. And in fact, it's about a 60-40 mix of students who are in residence in the school. I think 60% are in residence. Oh, no, sorry, 60% commute. They go home every day after school. They come to school in the morning, go home. There's a school bus, or there's a school bus. I think they come individually to school, and 40% are in residence in 4 different homes. So Future Hope started as a set of homes, as just actually shelters for homeless children from the streets of Calcutta. Absolutely, the children with it's a completely free school, which is very unusual in India. Completely free school, because it's funded by various foundation. They're doing remarkable work. They are doing absolutely remarkable work. The school is excellent in many ways, but including athletics. The students are really talented athletes. Some of them have represented India, sort of junior and sort of junior Olympic levels and stuff. They're really, really good. Anyway, it was really eye-opening for me to go there. I'm going to quickly check to see how our data transfer is going, and if I can. What we didn't get to do very much, or we didn't get to do at all today, is share some of the instrument control software that normally we spend most of the session doing that. But today, because of the clouds and because we were looking at older data, not data we're collecting tonight, it was unusual in that sense. And Rob, you can attest to that. You've seen, and Jamaica, you've of course seen sessions where it wasn't cloudy. Let's see. Let me just check to see how the whole transfer thing is going. Yeah, we're chugging along slowly but steadily. Did you have any questions for me? Any of you?
I have just one question.
Yes, please, Sunny.
When are you going to be back on Big Island?
I don't know yet. Sunny, I don't know yet because if back to the Big Island for an event that's different from observing, but my next observing on Keck is not going to be until the first half of 2024. In fact, very specifically, it's going to be between February 1st and July 31st, but they haven't announced the dates yet. They haven't announced that part of the telescope schedule yet. I'll almost certainly be back for that, but I just don't know when yet.
Okay. Please let me know because I'd love to come back and visit you down there.
Oh, thank you. Sunny, we can do one better than that. I of course would love to have you visit when I'm here, but we have other scientists also shadowing whose sessions get shadowed at Keck. We might be able to, have you come here sooner than that if there are other people who are going to be shadowed while they're observing at Keck. Is it easy for you to get over here?
Not exactly because we only have one airline on Molokai and flights can be expensive.
Yes. Okay. So some advanced planning would be helpful. Jamaica and I are of course trying to populate calendar. Jamaica's in Jamaica. I think there's a November 9th event, right? I think our shadow that Evan is running. But I don't know if he's physically coming here. Sometimes the shadow sessions are run from remote locations. But having said that, Kekoa, who you met the other day, Sunny, he has an open invitation for you to come and visit anytime. So I would say, let's do it like this. If you're on the Big Island next, with family or alone, whenever you're on the Big Island next, let us know in advance and we'll arrange for you to visit.
Okay, sounds awesome.
Definitely make that happen. Okay. Yeah, thanks, Shamika. Yeah, please, that would be great. Sunny, when you have a minute, drop me an email. Drop Jamaica and me an email. Yeah, Margaret's session will be using the same setup, different galaxy. We'll be looking at the triangulum galaxy, and the main interest are these X-ray binaries, so black holes that are being a black hole and a massive star in orbit around each other. That'll be the main kind of source there. It will still use multi-set masks, so most of the objects won't be those. Most of them just will be ordinary stars, but the main targets of interest, which are a handful in number, I think it's a few tens, they will be these what are called HMXBs, high mass X-ray binaries. That's what they're called.
So this galaxy has a black hole and a supermassive star orbiting each other.
So every galaxy, Andromeda is the one we're looking at now. We look at Triangulum at the end of the night. They have supermassive black holes at their center. But in addition to that, in the main body of the galaxy, not at the center, but the main body of the galaxy, there are not supermassive, but stellar mass black holes, few to 10 times the mass of the sun, that are in orbit around a comparable mass star, not a full mass star. And those are called high mass, where high mass refers to the star, X-ray binary, because they emit X-rays, binary because they are these two stars in orbit around each other. The action of the black hole is to suck material out of the massive star. And the friction of that material heats up the gas to the point where it emits X-rays. So that's why they're called high mass X-ray binaries, HMXBs. That's what the target of Margaret's session is going to be, starting a couple of hours, a little more than about 2 hours and 20 minutes from now. That's when she's going to start her part, the second half of the night.
So how long is tonight's observation?
For the first half, we'll go until 12:09 a.m., so 9 minutes past midnight, and then Margaret takes over at 12:09, and she'll go until about 5:30 a.m. or 5 something in the morning. She'll be on for a little under 5 hours. Sorry, a little over 5 hours.
Oh,
So total night is about 10 hours. Little over 5 for the first half, little over 5 for the second half at this time of year. A little bit later in the year, the nights get a little longer. A little bit earlier in the year, the nights are a bit shorter.
well, I'm thankful I'm on break.
Sunny, it was very good to see you. Not once, but twice. Once in Molokai and once here. So very good to see you.
Yes.
Raj,
my
I have
best
a
here.
question.
Yeah, of course, please.
So I don't remember M32. Is that a new discovery, or just more in the conversation, or am I just missing it from?
No,
10 years?
it's been around. So M31 was the 31st object in his catalog, M32 is the 32nd, triangular 33rd. But so M31, M32, M33 have been known for a very long time. It's also been known for a very long time that M32 is strange. It's a very unusual kind of galaxy. But off and on, people do these campaigns to try and understand M32's interaction with M31. And I know for me in particular, this is sort of my second shot at trying to understand M32. I had a PhD student several years ago who did some work. I had a couple of PhD students. The two of them did two slightly different kinds of work for their PhD thesis. But one of the science goals, was to understand M32. This was, I'm talking about back in the 20 years ago. So 2002, 2003, all the way up to 2008, these two students did their PhD thesis and they studied M32. 2019, rejuvenation of interest, different way of studying it. That's what's going on. So
Understand.
so it's been around. It's been around. It's been strange for a very long time. Sandy Faber, I know, had a postdoc at one point who was also trying to understand it. And it's pulling at its tail. Some people are pulling at its ears, and we're trying to understand different aspects of it.
Why did you characterize it as strange, though?
Its properties are very strange. It's very compact in size compared to the number of stars it has. It has a very high density of stars. One of the highest density of stars of any known galaxy.
Thanks.
So for the number of stars it has, so we don't understand whether that's something that is caused by its proximity to Andromeda. Did it form like that, or did it form differently, and did Andromeda transform it into something like this? So unfortunately, the fingers pointed at Andromeda as the culprit, one way or the other, for Andromeda, for M32. Ultra compact dwarf.
Can you say whether M32 and M31 are going to interact sooner than our galaxy with Andromeda?
Almost certainly sooner. In fact, we've already seen signs of interaction. This was Phil Choi's thesis from 2002, but we're trying to characterize that interaction better. That's one of the main purposes of tonight's observations and this series of observations that goes back to last year and even to 2019, trying to understand how the nature of the gravitational interaction between the two. But almost certainly sooner than it's already ongoing, whereas the Andromeda Milky Way galaxies are still far enough apart that there's no real significant distortion of one galaxy by the other. But M32's distortion has started, and we first measured it in 2002. It wasn't change over a human lifetime, but we first detected it in great detail in 2002.
Do you anticipate an interaction between us in your lifetime?
Us meaning
the Milky Way and Andromeda?
No, we're talking about billions of years for that to happen, unless there's a medical miracle. And you saw how bad I was at snorkeling today, so it would take a huge miracle to keep me alive for that long.
Understood.
So
Just checking the
you know,
time
if-
scales.
yeah, yeah, billion years, yeah, billion years. Yeah.
Thanks.
Something like 4.5 billion years is what I heard.
I love these perspectives. Okay, Eric and Deb are signing off. Thanks for the whole experience.
Thank you very, very much.
See you
Thank
next
you.
time.
Thank you so much for joining us. Yes, we look forward to seeing you again.
Absolutely. Good night.
Bye.
Aloha.
Aloha. Jamika, so we usually do calibrations at the beginning if we can, but if we run out of time, we'll do them in the after the night, so early hours in the morning. So on our very first, we didn't get access to the instrument until the skies were dark, so we went straight into science observations. Michael did the calibrations for us after the end of the night, or the end of our half night and the second half observers. So this is to answer the question you had in the chat. Yeah, the instrument is generally stable enough that getting calibration before night, if we were to do them after the night, we wouldn't see a difference. So either one is fine, but we don't need both. I think I'm going to stop the recording unless there are questions.